All right, so today we are really diving into a fascinating area. We're talking about neutrinos,
These are pretty cool, yeah.
those like almost mythical particles, right? That can just zip through like the entire Earth. Like
Yeah.
it's not even there.
It's basically empty space to them.
And we're not even just talking about any neutrinos, we're talking about the possibility of finding their like hidden twins, right?
Yeah, right-handed neutrinos.
Right-handed neutrinos.
Yeah.
Because the ones we know,
Right.
the ones we've seen, those are all
They're all left-handed,
left-handed, at least according to
at least according to the standard model.
the standard model, right?
That's our, yeah,
Yeah.
our blueprint for how the universe works.
Our blueprint. This is like the kind of the rule book for how we think
Yeah, it's the rule book.
every,
It's the physics rule book, as far as we know.
as far as we know.
Yeah.
But there are some like, I don't know,
There's some gaps.
gaps, some missing pages potentially.
A few missing pages, yeah.
And right-handed neutrinos, this could be on one of those missing pages.
Could be a big gap.
So okay, let's talk about what makes them so special, these right-handed neutrinos.
So, for one thing, the standard model, the thing that we just said is,
Yeah.
our rule book. It says that neutrinos shouldn't have any mass.
They should be massless.
Massless. But we've known for a while now that they actually do have a little bit of mass.
They do.
Tiny amount.
Which throws a wrench in things.
It throws a wrench in things.
Yeah.
It means there's something we don't understand.
Okay.
There's some new particle or some new interaction or something.
So that's kind of where this gets really interesting, right?
Totally.
Because it's like, okay, we have this model, we think we know how it works.
Right. Yeah.
And then there's this little crack.
This crack in the foundation.
And then it's like, well, how do we explain that crack?
Right, exactly. And so one way to explain that crack is if there are these right-handed neutrinos, which are basically heavier mirror images of the neutrinos that we already know,
Okay.
and the race is on to try to find these things.
So, and luckily we've built an amazing tool, which is the Large Hadron Collider,
That's right.
LHC. I always feel like, gotta say the abbreviation, everyone.
Do it. Gotta do it.
The LHC.
For those who are maybe just joining us, the LHC, this is like a giant underground tunnel.
That's right.
Essentially.
It's a big ring where we smash protons together at basically the speed of light.
Nearly the speed of light. I mean, this is like almost recreating the Big Bang
In miniature.
in miniature
Yeah.
in this tunnel.
It's incredible.
Okay, so how are scientists actually looking for these right-handed neutrinos? Because we're talking about particles so small and so, what's the word, elusive,
Elusive, yeah.
that finding them seems almost impossible. Like, I don't
Ah.
even know what's a good analogy for that.
Oh.
It's like trying to find a needle in a haystack, but the needle's invisible.
Okay. So, yeah, how do you even begin to go about doing that?
Right. So this is where this new research paper that we're going to be talking about comes in.
Okay.
What they're looking for is a specific signature, a specific thing that would tell us, aha, this is evidence for a right-handed neutrino.
Okay.
And that thing is what we call the tri-lepton signal.
The tri-lepton signal. That sounds like something out of Star Wars.
It does sound pretty cool.
So what are we talking about here when we say tri-lepton signal?
Yeah, so this refers to when we see 3 leptons, which is a type of particle, includes electrons and their heavier cousins, muons,
Okay.
and they come out in a collision along with some missing energy.
Missing energy.
That's right. Because these particles, these right-handed neutrinos, they interact very weakly with matter.
Okay.
So they escape our detectors without leaving a trace.
So it's like it's not even just a needle in a haystack. It's like a needle in a haystack that might disappear.
It disappears as soon as we look at it, almost.
As soon as we look at it, it's gone.
Right.
And so the physicists, they have to be like extra clever
Very clever. Yeah.
about how to like track this thing down.
Right, because they can't see the right-handed neutrino directly.
Right.
They just have to infer its existence from what's left behind.
And what's left behind is this tri-lepton signal.
That's right. These 3 leptons and some missing energy.
And that's where things get really complex, I'm assuming.
That's where things get really hard.
Yeah.
Yeah, because there are a lot of collisions that happen in the LHC.
And so there's a lot of data coming out.
That's a lot of data to sift through, and most of it is not interesting.
It's just noise.
It's just noise. Exactly. So they have to find ways to separate the signal from the noise.
So, okay, how do you even begin? It's like, trying to hear a whisper in the middle of a rock concert. Like, where do you even start with that?
Right. So they've developed some really amazing techniques. And one approach is to use what's called NREFT.
NREFT. Okay, that sounds pretty intense.
It's a mouthful.
It is a mouthful.
It stands for non-relativistic effective field theory.
Okay.
But essentially what it is,
Yeah, break that down.
it's a way for physicists to describe the interactions of particles that we haven't discovered yet,
Okay.
like these right-handed neutrinos.
So it's like we can't see them,
Right.
but we're kind of like creating this almost like a
Model for how they might
model.
behave
Okay.
if they were there.
So like a set of rules almost.
Yeah, like a set of rules
Yeah, right.
that might govern how they interact with other particles.
So using this NREFT, like this set of rules,
Right.
this model,
Yeah.
they're looking for this
You're looking for these tri-lepton signals
tri-lepton signal,
in the data. Yeah,
3 leptons, missing energy, all that stuff.
exactly.
Okay, but how do they know?
Right.
How do they know if they found something or if it's just
How do you know if it's real?
random? Yeah.
Right, and that's where statistics comes in.
Okay.
So particle physicists use a measure called the sigma level
Okay.
to determine how confident they are in a result.
So the higher the sigma level,
The more confident they are,
or more confident
that's a real thing,
that they actually found something.
not just a statistical fluke.
Not just, yeah, like a random blip in the data.
Exactly.
Okay.
So a 3 sigma result,
G sigma.
that's generally considered like pretty interesting.
Okay.
We should look at this more.
All right.
But 5 sigma,
5 sigma, this is like
that's the gold standard.
the holy grail.
That's when we pop the champagne.
5 sigma. Okay, so what are some of the ways
Right.
that they're really trying to get to that,
To get to 5
to
sigma.
that level of confidence?
Yeah, so they have to be really careful about how they analyze the data.
Okay.
They might look at specific ranges of energies
Okay.
of the particles or specific angles that they come out at.
So it's like really
You
being
got to be selective.
selective about.
You got to be smart about how you analyze the data.
Okay.
And they also use these sophisticated techniques, like one of them is called boosted decision trees.
Boosted decision trees. Okay.
BDTs,
BDTs.
which sounds very complicated.
It does sound complicated.
But all it is it's basically like a flow chart
Okay.
that helps you make decisions.
Right.
So it looks at all the information about the particles.
Okay.
And it says, okay, how likely is it that this event, this collision,
Right.
came from a right-handed neutrino?
So it's almost like giving the detector
Giving them a sixth sense.
sixth sense to be like,
Yeah.
hey, look over here. This is interesting.
Exactly.
Okay.
And these BDTs, they're really powerful
Okay.
because they can find patterns in the data that humans might not be able to see.
That's wild.
It is wild.
But also really cool
Yeah.
because it's like we're using, I mean, we're
The power of computers
the power of computers
Yeah.
to help us
to find these tiny little
with
particles.
these tiny little particles. Okay.
And it's not just about the BDTs.
Okay.
It's also about, they have to consider all sorts of possibilities.
Like what?
For example, the mass of the right-handed neutrino.
Okay.
We don't know what that is.
We don't know.
It could be really heavy. It could be really light.
Okay.
And depending on what its mass is, it's going to leave a different signature in the detector.
So it's like, it's not even just finding, like we were saying, the needle in the haystack.
Yeah.
It's like the needle can change shape.
The needle can change.
Their size.
It can be a different color.
Oh my gosh. Okay.
It could be anything.
All right. So they have to be like extra
Extra clever.
on their toes
On their toes, yeah.
about like how to even like pinpoint this thing.
And be ready to adjust their search depending on what they see in the data.
Okay. Wow. This is really
It's cutting edge.
cutting edge.
Yeah.
I mean, this is high stakes physics right here.
Absolutely.
Because if they find this
It changes everything.
changes everything. So, okay, let's talk about that.
Huh.
For those of us who are not particle physicists,
Yeah.
why should we care? Why is this so important?
That's the million-dollar question, right?
It is the million-dollar question.
Why should anyone care about this?
Why?
Well, I mean, imagine finding the missing piece of a puzzle
Okay.
that unlocks a whole new understanding of the universe.
Okay, I'm listening.
That's what this is.
All right, give me the big picture here.
Okay, so for one thing, these right-handed neutrinos,
Yeah.
they can explain one of the biggest mysteries in astrophysics,
Right.
which is dark matter.
Wait,
Yeah.
are you saying that these tiny little particles
They might be
can
connected
explain something as massive
as massive and as mysterious as dark matter.
as dark matter? Oh.
There are theories
Wow.
that connect right-handed neutrinos to dark matter.
Okay.
And that's not all.
There's more.
There's more. Finding these particles would also tell us something about the origin of neutrino masses,
Okay.
which is something that the standard model, again, very successful theory, but it can't explain.
it can't quite explain that.
Right.
It doesn't quite get that right.
So we're talking like rewriting the textbooks here, potentially.
Potentially rewriting textbooks.
Wow. It's like these particles, they're like this thread.
Yeah.
And if we pull on that thread, it's like this whole...
It unravels the whole thing.
It unravels this whole, like, our understanding of the universe.
Exactly.
This has been an incredible deep dive so far.
It has.
But I have to ask, like, for you, what's the one question that really sticks with you?
Oh, that's a good one.
After going through all of this research.
Wow.
Yeah. It's really mind-boggling to think about how much these tiny particles, these neutrinos, might actually influence our understanding of, like, the entire universe. Yeah. But before we get, too far down the rabbit hole here,
right.
I'm curious, for you, like, what's the one question that really stuck with you?
Oh, that's a good question. After going through all this research, what's the thing that you just keep coming back to?
There's this idea of symmetry in the universe that I think is really, really interesting.
Symmetry. Okay, tell me more.
Yeah. So
what does that have to do with these right-handed neutrinos?
Well, in physics, we often find that for every particle, there's an antiparticle. It's kind of like a mirror image.
Okay.
And the same is true for the forces. So, like, there's the weak force.
Right.
And that's governed by these particles called W bosons. And W bosons, just like a lot of particles, they have antiparticles.
Okay.
Which are their own little kind of evil twins.
Right.
And so...
So where do right-handed neutrinos fit into this?
So that's the thing, right?
Yeah.
We've only ever seen left-handed neutrinos.
Oh, wow. So it's like this weird...
It's this weird asymmetry where's the right-handed neutrino?
It's like the universe has a preference for left-handedness when it comes to neutrinos.
Yeah, we don't know why that is.
That is bizarre. It makes you wonder, like, is there some deeper reason why we haven't found them?
Right.
Like, are they truly absent?
Right, or are we just not looking in the right way?
Or, yeah, are we just, like, totally missing something?
Exactly.
Okay.
And that's what's so cool about this research.
Yeah.
Is that if we do find these right-handed neutrinos, it's not just like, oh, we filled in this little gap in our knowledge.
Right.
It might actually change our understanding of...
fundamentally change how we think about...
how the universe works at a very fundamental level.
Wow. It's like, it's almost like we're on the verge of this, like... new era.
It really feels that
of physics.
Yeah.
Where, it all hinges on finding these incredibly tiny particles.
Like Jerring's, yeah.
This has been incredible.
It's really cool.
Thank you so much for taking us on this deep dive.
My pleasure.
Into the world of neutrinos.
Yeah.
Right-handed and otherwise. And for everyone listening, thank you so much for joining us on this journey into the subatomic.
Yeah. Thanks for listening, everybody.
And remember, sometimes the smallest things can lead to the biggest discoveries.
That's right. Keep looking up.